Right, so yesterday we talked about melting, boiling. We started talking about melting, boiling, and evaporation. We talked about changes of state, going from solid, liquid to gas, and reverse. We talked about the temperatures at the change of state, so the melting temperature and the boiling temperature, or the freezing temperature and the temperature at condensation. Right, and how for pure substances, those are very specific temperatures and they do not change during the change of state, right? But only after. Okay. Now, right, if you plot a curve or if you plot a graph of the melting and boiling of any substance, right, it will look something like what I will attempt to draw. So let's take lines. Okay. And so what you have, you on the y-axis, you're going to have temperature. On the x-axis, you're going to have time. And let's say you are heating something, right? And so this is, well, for something general, right? Let's say I'm not putting any values for temperature, but what it's going to look like is you're going to start with an increase in temperature, and then it's going to level off for some time. Then it will start rising again, and then it will level off again, then it will start rising. Okay, now obviously the leveling off is not very flat. So what you have at this point, you've got a solid, right, and the temperature is rising. Now that the temperature is stable over a period of time, this is the melting point. And the melting point is actually the temperature, right? So this is the melting point. And the solid is melting. Once it's melted, it's become a liquid. Over here, you have a liquid with the temperature going up. Then, right, this is the boiling point. So over here, boiling is occurring, and obviously a change of state, right? So it's going to a gas, and now it's a gas. Just because it's turned into a gas doesn't mean you can't continue heating it. Of course, issues with temperature and pressure and volume will all come in when it changes to a gas, what we've already covered in previous chapters. So this is what a curve will look like if you start with a solid substance and you heat it. You turn this upside down and you get a cooling curve. So this is a heating curve. You take this the other way. And you start from here, for example, at some temperature. I should probably do this in parts. Now again, right, what substance this is, what the temperature is, that is not of concern. What's of concern is the trend. Okay, so you've got a gas. Again, on the y-axis, you've got the temperature. On the x-axis, you've got time, right? And temperature in degrees centigrade and time in minutes. Okay, so over here as well. And so you've got a gas that you're cooling, it's coming down. Over here, condensation, right? And so this is the temperature where you would say, oh, it's condensing, right? And this temperature, and I'm not comparing it to this graph, obviously, because I haven't drawn it the same way. But for any substance, its boiling temperature and the temperature condensation, as I explained yesterday, will be the same. It just depends whether you are giving an input of energy and making the temperature rise, or you are taking energy away and making temperature fall, right? But that temperature at which the change of state occurs is the same, right? So in case of water, it will be 100 degrees centigrade. Then you've got a liquid. You've got temperature going down, and you've got freezing, right? And for any substance, if you take a note of the temperature, right, the freezing point will be the same as the melting point, right? And you can see that for this stretch, the temperature is not changing because a change of state is occurring, right? And so that is something you will notice for any pure substance. And now you've got a solid. You can continue cooling it, right? No one's stopping you from continuing to lower the temperature, but of course there will not be any further change of state. Any questions?
No.
Right, so this is a cooling curve. Now, what would you get on a side if you had impurities or if you had a mixture? Right, so if you start heating something with impurities, you'd get something like this. Right, now how many bumps it has depends on how many impurities there are, right? But you've got this little over here, and then this, and then perhaps this, maybe, right, something over here. And so, right, this is in the case of impurities or mixtures. And I'm just giving you an idea, right? It's not exact. Obviously, you're not talking about any particular melting or boiling point, right? You've got temperature, degrees centigrade, and time per minute. So always label your axis. And so you won't get a very clear melting or boiling point. You won't get a very distinct curve or graph in this case, right? It will be staggered. It will have multiple points where perhaps one of the substances is melting, right? And then the next, and then the next, right? And then same case when it reaches to perhaps the boiling point. So this is what you would observe. And that's why, right, the melting point and boiling point of pure substances are distinct, right? They're very clear. They are, right? They show up very clearly when you plot this. Yes, Hara.
Like do substance with impurities take more time to freeze or
I mean, if you're talking about water in specific or other impurities, yes, it lowers the freezing point, right? So if you add salt to water, it will not freeze at 0 degrees centigrade. It will freeze at lower than 0. And that is actually a technique used in countries where it snows a lot to clear pathways, to clear the road. They add salt to the ice, and so, right, it melts even though the temperature is very cold because it's snowing. right? But because the freezing point of the ice has been lowered further below zero, and so it melts, it turns into water, and that water washes away, and that clears the paths or the roads or whatever they're trying to do. Similarly, it raises the boiling point, right? So if you're trying to boil salt water, it will not boil at 100, it will boil at higher than 100. Okay?
Yes. Thank you.
All right, what do we have next? Now, the next topic, right? Uh, Latent heat of fusion is not part of the IGCSE syllabus, right? And what else? Let me just check once again. Neither is latent heat of vaporization. So the next two topics that I'm going to discuss, they're short topics, but still, right? They're part of the O level syllabus, not for IGCSE. So what is latent heat of fusion? Let me put on right that. Why does this keep changing? I don't know. Yeah, good. So so it is the energy transferred to a solid during melting, or it is the energy given out by a liquid, right, during, you can say, freezing or solidification. So it's turning into a solid. Depends on which way you're going. You're putting in
Uh,
energy. Yeah.
Isn't it the same as exothermic and endothermic changes?
It is, but exothermic and endothermic is, I guess, used more for reactions,
Okay.
right?
Yeah.
Whereas, right, so when you're heating something, it is endothermic because you're supplying energy for a change of state. Whereas, right, if you're going from solid to liquid to gas, but if you're going in reverse, then that is exothermic because they have to lose it,
Yeah.
right? So latent means hidden, and fusion means melting. Right now, going both ways, they're not giving separate names for the right reverse. And so the latent heat, right, we're going to do latent heat vaporization as well after this. So the latent heat, whether you're talking about fusion or vaporization, right, it does not cause a temperature change as we've already talked about. Right, and it seems to disappear. Now, where it goes, we will see later. Right, obviously, it's not disappearing, so something's happening. Next, we've got latent heat of vaporization. Now, you can guess what this one's for. So, latent heat of vaporization is the heat or energy, right, needed to change a liquid into vapor, or the reverse. So going both ways, right? And again, right, it does not cause a temperature change. So, right, when you have water that's boiling and you stick a thermometer in it, it will continue to show 100 degrees centigrade, right?
Hmm. Um,
Question?
can you please explain it again?
Like which part?
Latent heat of vaporization.
Okay, so obviously when a change of state is occurring, energy is being put in, right? In case of going from liquid to vapor, you are adding energy, right?
Yeah.
In case of going from a gas to a liquid, energy is being removed, right? So in both cases, the energy that needs, like the term latent heat of vaporization is used for both cases, right? So the energy required to take a substance from its liquid to gaseous form, right? That energy is called the latent heat of vaporization. And to cool a gas to its liquid form is also called the latent heat of vaporization, just like we did for latent heat of fusion, going both ways, solid to melting and liquid to solidification. So it goes both ways. And again, with the temperature change, right, when a change of state is occurring, the temperature will not change, even though you are supplying energy, right? So you're constantly supplying energy to water, right? It's boiling, it's turning to gas, right? So energy is being supplied, but the temperature will stick at 100 degrees centigrade until all the water has turned to gas. It will not, the temperature will not go up. Okay?
Yes.
Okay.
Like boiling can be an example of both of these, no?
Hmm?
Boiling can be an example of both of these.
Yeah. Boiling, the energy required for boiling to occur is an example of the latent heat of vaporization. Right? Now keep in mind, right, although the temperature does not increase, the energy of steam, for example, right, we're just keeping it simple, is more than the energy of boiling water. Steam, because it is turned to gas, has more energy in it than the water that is boiling. Why? Because a change of state has already occurred, right? So this has more energy. It's not causing a temperature increase. You won't notice on thermometer, but that energy is going somewhere. That energy is going into causing the change of state, right? And so steam, because it is at the high, it's the upward trend of change of state, right? And so this has more energy. So, right, getting burned by steam is actually worse than getting burned by hot water or boiling water. This is not like, obviously it's not comfortable, but uh, uh, getting scalded, I believe, right, by steam is worse. Why is it worse? Because it has more energy, so it's going to burn you even, worse than water. It's
But like we take steam on like almost daily basis,
that you're taking
and
very,
like
okay, so you're taking low amounts and you're breathing it in, and that too, if it's right, the steam that you're taking in is mostly the steam that is before boil. So you're not taking in the steam from boiling water, right? So it's basically what you're taking is the water vapor, the hot water vapor, due to evaporation that's occurring before the boiling of the water. If you're going to, I wouldn't recommend you trying it, but just try placing your hand over the steam that's coming out of boiling water. It's going to be super hot as compared to
like,
the steam you take from just heating water to 60 or 65 degrees centigrade. That is not boiling. That is evaporation that's happening. Okay.
Yes.
All right. So these two topics were not part of the IGCSE, as I mentioned. The next one is, so, right, we're going to refer back to the kinetic particle model and talk about, right, what's happening with the changes of state. Right, so what's happening with melting and solidification? Right, when you're talking about the latent heat of fusion, what's happening? So the energy is being used to weaken the attractive forces between the particles. In case of melting, and so that they overcome those intermolecular forces and are able to move about, thereby causing a change in state. Their vibrations also increase. And so they're able to move about more, and and that brings about a change in, so they're able to get far enough to be able to move around one another and turn into a liquid. So change of state. So that's where the energy is going. Right? And in case of solidification or freezing, when the energy is lost, right? So in case of solidification, right, thermal energy is lost to the surroundings, or whatever's around, and so the particles lose that energy and they come closer, and so the intermolecular forces take over again, and so that change of state occurs. Now what's mentioned over here, that what's actually happening is that when you're using energy to cause melting, is used just a sec, sorry, used to increase the potential energy of the particle. So that is delta EP for potential energy, but not their average kinetic energy. Because if their average kinetic energy would increase, you'd notice an increase in temperature, and that's not happening. And so what's happening going from solid to liquid is that the potential energy of the particles during that change of state is going up, and so they're moving further apart. The intermolecular, they're able to overcome the intermolecular forces, right? And the change of state is occurring. And the reverse, when going from liquid to solid, they are losing that potential energy and coming closer. The intermolecular forces are taking over again. They're holding them in place, right? And so they become a solid. Any questions?
No.
Aram? All good, I guess. Okay, next up, vaporization and condensation. So pretty much the same thing. So there's still some intermolecular forces between the particles of a liquid, and so the liquid particles, when they're being heated, right, gain energy. So again, in this case, their potential energy to overcome the forces holding them. And move freely as gas particles. Right, again, their average kinetic energy is not going up, because if that would happen, it would cause a change in temperature, and that's not happening. Right, in this case, the energy is also required to push the surrounding atmosphere away, because there's an increase in volume. So the energy also required to push, right, the surrounding environment, right, because there's an increase in volume when going from liquid to gas. Right, so there's expansion. On the flip case, when going from vapor to liquid, right, the particles lose potential energy, come closer together as liquid molecule, as particles of a liquid. Right, and again, right, the energy that is being lost is transferred to as thermal energy to the surrounding. Any questions?
No.
Okay. Next up, something that I have covered earlier on, but since it's given here, boiling and evaporation. So boiling and evaporation. So at standard atmospheric temperature, right? The boiling point is for water is 100 degrees centigrade, right? Now, for a pure liquid, boiling occurs at a definite temperature, right? And what happens is you've got bubbles that form within the liquid, right? And these bubbles are basically, right, the gaseous or vapor form of the particles, and they come up to the surface and escape. And so the water will continue to boil until all of it has happened. Okay?
Yes.
Okay. Now, evaporation, right, does not happen at a fixed temperature. So it doesn't need to be at 100 degrees centigrade. So just like we talked about earlier, the steaming that you do during winters, whenever you have a cold, or for any other reason. So, right, does not need a fix, or does not have actually a fixed temperature. It can occur below boiling point and does occur. And basically what's happening over here is a few energetic particles. So few particles that have more energy than the rest. The rest what am I writing? Energetic particles close to the surface of the liquid escape and become gas particles. Right? And this occurs at all temperatures. So what happens when you're steaming something, when you're taking steam and you're heating your, pot of water on a flame or a stove, right? So you've got water here and you've got your flame over here. And so obviously the particles closer to the heat source at the bottom will gain more energy as compared to the rest of the liquid. And so when they have more energy, they will rise and they will escape the surface as steam, even though the temperature may be 65 degrees centigrade. And so that's still 35 degrees centigrade below boiling. So that's how you get your steam. But if you boil the liquid for your steam, then that's going to be problematic. Now, conditions affecting evaporation. The temperature, the higher the temperature, right, the more evaporation. Because obviously the particles will have more energy, they'll be moving faster, they'll escape the surface of the liquid easily, right? So more energy, faster, escape easily.
Does evaporation occurs below the boiling point or above the boiling point?
Look, once you've reached the boiling point, then whatever is happening is boiling. And evaporation does not occur for gases. So once all of it has turned to gas, you're not going to say, oh, the gas is evaporating. No, liquids evaporate. Okay, so evaporation is what occurs in a liquid below its boiling point. At its boiling point, it's boiling, it's not evaporating. Right? How do you think when clothes dry when you put them out in the sun or under the fan? The water in the clothes does not boil. Right? So if you put it out in the sun, because the sun rays, they're hot, obviously the sun has heat as well, and that heat is being provided to the earth. And so the clothes are constantly out. Like you can even like if you keep standing out in the sun for in one position, you start feeling extra hot. Why? Because that same point on your skin or on your body is being exposed to heat, so it's getting hotter and hotter and hotter. And that's what's happening to clothes. So when the water in those clothes are gaining that energy, they're escaping from the surface, even though it's not boiling. Okay. Then, right, when the surface area of the liquid is large. So you've got a glass of water and then you've got like a trough of water. Water will evaporate faster from the trough than from the glass. Of course, keeping in mind that the volume is the same in the both. If you've got more water, more volume of water in the trough, then you might not notice the difference because there's more to go with. But why? Because there's more surface of the liquid available for the particles to escape from, as opposed to just this. So maybe two particles can get out of here. You got a lot more going on over here. Then, right, if there's a wind blowing, or oh, by the way, how do you think you pronounce this?
Drought.
Hmm?
Drought.
Adam?
Drought.
Draft.
White.
Draft.
Draft. But like it has a G and H in
Yes,
it.
but that's how you pronounce it.
Well, that's weird.
English is weird. Okay. So if there's a wind or a draft blowing, that will speed up evaporation. Right? And the reason for that is because any vapor particles, right, will be carried away and that leaves room for other energetic particles of that liquid to escape as well, and also prevents the vapor particles from going back to liquid form. Why? Because they've been taken away by the wind. So wherever they're going, they're not going back to that same liquid. Okay. Now, just a bit left for this chapter. Cooling by evaporation. Basically, the concept over here is, right, for example, right, you want like evaporation causes cooling. How does it cause cooling? Right? Because, for example, you've got sweat. When you sweat, The reason you sweat is because it is a response of the body to lose heat and cool down. Okay, how does that happen? Well, the sweat covers the body, or let's say liquid, right? It takes energy from whatever object it is, right? And then it evaporates, taking it, right? It becomes a high energy liquid particle and evaporates. So it takes the energy to evaporate, thereby causing cooling. Does that make sense?
Yes.
Hara?
Yes,
Right?
but
And so the object now has lesser energy, right? Which basically means now a lower temperature. They talk about an experiment which you can read about, okay, in the text. And okay, cooling by contact. So that's right. The last thing, I guess. So when cooling occurs, right, it causes temperature decrease even in the liquid itself. So for example, you've got a body of liquid, right, and evaporation occurs, and so we know, right, whatever particles with high energy they're going to leave. And so what that does is that the remaining particles have a lower average kinetic energy, right? And so the temperature, that's how cooling occurs, the temperature falls. So if another object, we also learned that temperature, thermal energy flows from a hotter to a colder object. We've learned that. Right? And so if you've got another, right, hotter object, for example, or let's not say hotter, let's just say another object. In contact with a liquid that's cooling, sorry, evaporating. As the liquid continues to evaporate, it will cause the object to cool. Why? Same thing we discussed over here, right? Same thing we discussed about the body and sweating. That is a perfect example for this. Your body is the object that is contact with the liquid, which is the sweat. The sweat is evaporating, it is cooling the body. Questions?
can you give an example?
Another example.
Yeah, like the drying, like how the clothes dry.
Okay. Another example, you've ever been to the doctor to get your a blood test or something, and they use an alcohol swab that that little patch that's wet and they rub it on your skin. Have you ever experienced that?
No,
No, you've never been to the doctor.
no,
You never had a blood test or an injection.
no.
Oh my!
Like uh, एक दफा while I was young, I guess.
Do you remember anything about it?
No,
Okay,
I think
right.
I was 5 to 6.
Okay, so alcohol swabs when they rub it on the skin, right? Your skin starts to feel a bit cool. Why? Because the alcohol is volatile. Right now, what does that mean? That it very quickly evaporates, right? And when it evaporates, the part of the skin where it was put, where that swab was rubbed, feels cool. Why? Because it took that energy from that part of the skin, immediately evaporated. So volatile, right? Just a little bit of heat and it's gone, it's turned to vapor. It cools your skin. Similarly, for perfumes that are alcohol based, have you ever used those?
Yeah,
If you apply that directly to your skin, after a while or maybe immediately, do you feel it that that part of your skin is a bit cool? You do feel that cool sensation,
yeah,
right? Same concept. It's alcohol based. The alcohol is volatile. It immediately or very quickly it evaporates due to the body heat, and that part of your right skin starts to feel cool. That's evaporation, and that is the cooling effect of evaporation. Okay.
yeah.
All right, and we have reached the end of this chapter. So congratulations. Now I want you, I'm going to put this on screen. I want you to read the next chapter as homework for next time. All right, so this is the IGCSE book, right? Same for the O level. So chapter 2.3, transfer of
We have
thermal
to,
transfer of thermal energy.
we have to read that.
Yes, because it's pretty straightforward. There is a bit of concept involved, but it's very straightforward. If you read this, it will make explanation easier and it will make classes go faster. I won't have to spend too much time on this. So conduction, convection, and radiation,
Those three we have to read that part.
right? There is also consequences of thermal energy transfer. You can see there's no calculation, nothing. It's just a bit of concept and then examples. Okay, so I actually want you to read the entire chapter, not just one part. Conduction, convection, radiation, and then consequences of thermal energy transfer. Right? it is not challenging. At least give it a read once so that you know what it's talking about. And right, so I can go relatively quickly over this chapter, not having to go into too much detail because you'll be familiar with it. Okay, well, not detail, but not going into too much explanation because you'll be familiar with it. And so we can end. This is the last of thermal physics, and then we can move on to section 3, which is
Wait.
waves.
Okay.
All right, so what do you think? Will you guys be able to do that?
Yeah,
We can try. Yeah.
I have a yes and a try, so I'll take that as a yes.
I'll try.
Yes.
It's not a no, but I'll try. It's not a yes either.
If it's not a no, it's a yes.
And it's not a no either.
Okay.
Yeah.
So yeah, that's all for today, for this week, and I'll see you guys next time, inshallah.
Sure.